Okay, in this video, we take a look at problem number 11 of chapter 14. Always a difficult problem. I think it's worthy of a problem in which a video solution would be helpful. So let's go ahead and try this one. It's a uniform meter stick of mass M pivoted on a hinge at one end, held horizontally by a spring with a spring constant K attached to the other end as shown in this figure. If the stick oscillates up and down, what is its frequency? Write a torque equation about the hinge. That's the hint. Now, this is listed as a level 2 problem, but certainly is a challenging one. So oftentimes we can tell by looking at the Roman numerals there just how difficult these problems are. But this one I think is actually worthy of a level 3. So let's go ahead and take a look at how we might solve it. Before I begin, I want to go back to this portion of our unit on simple harmonic motion. When we looked at applying Newton's second law for a mass in a spring, because we have that restoring force for a simple mass in a spring equal to negative kx, we had to write a differential equation. This came from F equals m times a. Just to refresh our memory, F equals m times a, and we said that that case was equal to negative kx. And when we go through and write that as ma plus kx is equal to 0, we can write that as m second derivative of x with respect to time plus k times x is equal to 0. And then, sure enough, just dividing everything by m, we have this. So just a quick refresher on what we did from before. When we went through and looked at the solution, we found that the solution to this was a sinusoidal in form, showing that x is equal to some a cosine omega t. We said that this equation was satisfied only if omega squared was equal to k over m. And we went through and also found we could write both the frequency and the period is just a 1 over 2 pi square root of k over m, or 2 pi times square root of m over k. Now, the reason I'm showing you that is you see that our solution here for this particular oscillator is very similar to what we had on the other one. This is more complex because it's not a simple mass in a spring. It's a bar that's going to be rotating about some pivot. We're going to have to use moments of inertia here instead of just treating objects as point objects like we did before. So that's where it gets a little bit more challenging. So let's go ahead and start by writing a torque equation about the hinge. Let's see where that leads. And so I'm going to go ahead and redraw this down here, similar to what I have above, but let's go ahead and change this a little bit. We have this bar that's being currently held in place, sort of in a state of equilibrium by that spring. And let's see. The spring has some initial stretch. And that initial stretch is from its relaxed length, right? So if I think of this as the relaxed length of that spring, then this thing is already stretching a little bit. Let's just call that y naught. How far it's stretched a little bit is because that spring is stretching to support the weight of that meter stick. So let's go ahead and draw some things in here. We have the weight of that meter stick assumed to be concentrated at the center of gravity. Let's go ahead and put that here as mg. And I guess this is using capital M, so think of that as big M times G. That's at a distance L over 2 from the fulcrum. Now this is 1.25, but I'm just going to change that to L. So we do a variable solution here. And so that center of gravity producing a torque about this point that's clockwise, so mg L over 2. And then, of course, the spring is going to have to exert an upward force to sort of maintain equilibrium there. Now, that force is twice as far away from here. And if you remember that torque is force times distance, the torques have to balance. And so that force would end up having to be half as big as this one here. But let's go ahead and write some equations that sort of show that. So sum of the torque about any point is equal to 0 because it's in a state of rotational equilibrium, right? For this particular spot, alpha is equal to 0. It's not accelerating right now, state of equilibrium. So those torques can be written as mg L over 2. It's the torque about that point due to the weight. And then minus a counterclockwise torque. Let's see, that'd be the force from the spring times how far away that is, and so that would be L. Okay, and we remember that for a standard spring, we say that for a standard spring, the force is in the form of negative kx. Well, here we're using y naught to represent x, and we'll let that k stay as it is. So mg L over 2 minus k times delta, times y naught times L is equal to 0. Now I'm going to go ahead and just write this as k y naught L is equal to mg L over 2. Now I'm going to end up using this a little bit later on, so I'm just going to go ahead and circle it. And we'll come back to that equation a little bit. I see that I could do some additional things. I could cross off the L's here. I could try to solve this for maybe y naught or something along those lines, but I'm just going to leave it as it is right now. Now, this next part, we're going to go ahead and displace this thing further downward. I'm going to, once it's in a state of equilibrium, I'm going to displace it a little bit more. And so let's just go ahead and draw that on here as a change to this. Now I'm going to go ahead and stretch this thing down just a little bit further. Another important part of this is that this is for a slight angles here, right? So some of you may have recognized that force there, mg, is acting at a little bit of an angle from the horizontal here. So I can't say it's 90 degrees, and I'm sort of approximating this using small angle approximations. So I'm not going to be concerned with the direction of that force in relation to that lever arm, right? I'm just going to say it's a really small oscillation, and so we're going to sort of ignore that little portion. Okay, so that makes it actually able to be solved. Otherwise, it'd get quite challenging to do. As if this wasn't challenging enough already, you say. All right, let's take a look at second part. I pull it down a little bit further. I stretch it another distance. I'm going to call that delta y, which means the force from the spring is going to have to increase a little bit, right? So that force becomes a little bit bigger. I've stretched that spring further. When I let this thing go now, it's going to oscillate up and down, just like a typical mass on a spring, with some frequency. And that's my goal, is to come up with that equation. Now we're going to again use the sum of the torques about this hinge is not equal to 0 now. Here it was equal to 0 because it was in a state of rotational equilibrium. When that torque is unbalanced, it produces an acceleration according to Newton's second law, right? So net torque is equal to I alpha. And so let's go ahead and write what that is using the forces that are acting here. So mg L over 2, that remains as it is. And now I have this force over here minus the force from the spring times L. Okay, let's go ahead and just keep going there. So the force from the spring, we can write that as K times, I see that the total distance that I've stretched that now is y naught plus delta y. Okay, and let's go a little bit further here. And I recognize now, I have an expression down here for k y naught L. K y naught L is mg L over 2. So let's go ahead and replace k y naught L, that term right there, with mg L over 2 and see what happens here. And sure enough, you see that these two things sort of reduce right out. And so that's nice. We can sort of think of that as some initial torque just to begin with, to hold it in a state of equilibrium. Really doesn't affect the overall final answer. It's sort of like it's what I had before, it's what I have now. So those two terms sort of reduce out. And I get an equation that's a little bit more manageable. I alpha is equal to, let's see, negative k. Now before I put in delta y, I know I'm going to try to get to a form like this here. I'm going to try to replace y, delta y, with some portion of theta, right? So just like we had from before, we're going to try to write this in terms of theta. So let's take a look at this over here. Sort of running out of colors there. Apologize for this. Can sort of think of this. Blue is really close to purple. Give me something different here. Let's try pink. Can sort of think of this as almost a version of a right triangle, right? Almost. And I'm looking for this length over here, right? Looking for this this delta y. I can sort of think of that delta y. It's like how far down I'm pulled here, right? That little distance there would be equal to, let's see, delta y, equal to L times the sine of theta. And again, you sort of hard to tell up here, but if I think of this as a right triangle, this is the side opposite of that angle theta, and I can say if that's L, that would be delta y is equal to L sine theta. And for small angles, even more approximations. For small angle, the sine of theta is approximately equal to theta, right, for small angles. Okay, so let's go ahead and replace that. Let's go back to purple. Minus k delta y times L. So delta y can be thought of as L theta and then times L. This portion right here is always a sticking point, so always difficult to sort of see how we got to that. Okay, I think the rest of it's fairly straightforward, but this is a little bit challenging, which is why I think an equation, video solution rather, is useful here. So I alpha equal to, let's see, that'd be negative k L squared theta. Okay, now still doesn't look like much, but let's remember when we went back to this thing here that we had to sort of write a second order differential equation to get us to the point where we're going to come up with our solution. So we can do the same thing here with alpha. I can write that as, let's see, I times the second derivative of theta with respect to time. Bring that over to the other side. I get plus k L squared theta is equal to 0. And just like we did before, we like to have this first term have a coefficient of 1. So let's divide everything out by I. And let's replace I with I for meter stick is about the endpoint is 1/3 ml squared. So replacing I with 1/3 ml squared times theta is equal to 0. And I'm going to have to switch over to white here since I'm onto the other portion of my board, but we can do that. Plus, let's see, the L's reduce out and I get k over 1/3 m. Well, that's 3k over m times theta. And sure enough, this equation is very similar, almost identical to this equation that we have here, right? Where k over m, remember that was related to omega. Omega squared was k over m. Since we have a differential equation here that looks very similar to what I had before, this is the same kind of solution. We see that omega squared must be equal to 3k over m in order for our equation to be satisfied, where theta can be written as a times the cosine of omega t. Omega squared must be equal to 3k over m, or omega would be equal to the square root of 3k over m. And since that's equal to 2 pi f, we can of course write that as frequency equal to 1 over 2 pi square root of 3k over m, the solution I was looking to obtain. And there we go. I hope the video helped.